Hi all, I'm Glenn, and I'm going to talk about GeckOS, which is a Unix-like operating system for Commodore 64 and a couple of the other Commodore machines. I'm a 64 guy, and my interest is programming languages and operating systems. I've got a good collection, a lot of it's on my website there. And I talked at a lot of the Commodore shows. I talk every year at VCF Midwest, and I've spoken at the one of the Las Vegas shows, the old C4 show, and of course I've spoken at the premier Commodore conference, which is of course World of Commodore here in Toronto. Yes. Although I do have to say, Father forgive me, it has been 5 years since my last World of Commodore, right? So I don't know how many Hail Jack Tramiels I'll have to say for that. But, and most of the talks I've given have been about programming languages. Although I've talked a couple times about operating systems, but it's always been GS. So I said to myself, you know, there are other operating systems out there for the Commodore 64, and I should probably learn one and share some knowledge about it. And so I looked through my collection and I decided I was going to talk about GeckOS, which turns out to be a really good choice because, of course, this year is the 50th anniversary of UNIX, which of course is why Dennis Ritchie and Ken Thompson have their party hats on. And nice machine, huh? PDP-11 Model 20. Oh, that's a pretty big honking machine there, even for the early versions of UNIX, right? So if you look at that, and then you think to yourself, UNIX on a Commodore 64, well, you might be forgiven if you had a reaction like this. Right? But let's stop and think about it for a minute. Is it really that crazy? Right? Let's, let's face it, you're not going to get Solaris or Linux or BSD or anything like that running on a Commodore 64. But you might get something like the earlier Unixes that weren't quite as large as the modern ones are. So let's look at the machines that the early versions of Unix ran on. And by the way, these numbers come from Brian Kernighan's new book on the history of Unix. Anybody read that yet? Yeah, if you haven't read it, go out and get it. It's a great book. But the first version of Unix was written on a PDP-7. And that thing had 16 kilobytes of memory. Now that's not an exact number because the machine had 18-bit words and so forth, but I mean, think about that for a second, right? And then about a year later, they ported it to C language, and they ran it on that big honkin' PDP-11 you just saw with 24K. Good Lord, wow. On a Commodore 64, we have, well, 64K. Yeah, okay, we're covered in the memory department, right? How about processor speed? Well, that's a little harder to compare because the machines are really very different, and you can't really make an apples-to-apples comparison. But from the research I did, I got the impression that they really are comparable in speed between a Commodore 64 and that PDP-11. But somebody might contradict me online, I'm sure, but at least it's in the ballpark, right? So memory, processor speed, yeah, not that far away. However, the CPU itself, that's where the comparison kind of falls down, because there are three big differences between the PDP-11 and a 6510. First of all, the PDP-11 had a user mode and a kernel mode. So there was some protection when the kernel was running that user programs couldn't stop all over it. And of course, there's nothing like that on a 6502. We don't have, ring 0 and ring 3 or anything like that. And second of all, the PDP-11 had 8 16-bit general registers. Okay, what have we got on a 6502? We have these 3 little tiny 8-bit registers, right? Accumulator, X index, Y index, and those are not general registers. They all answer to different instructions, right? So, yeah, the coding is going to be difficult. And the third thing, of course, is the stack. PDP-11 had a register that said, this is where the stack is, which is what you need for multitasking because, of course, every program has to have its own stack. So it's a simple matter to just change the value in that register and say, oh, well, now the stack is over here. Let's go over and run this program, right? Nothing like that on the 6502, of course, where the stack is always at 0100 and there's no way to change it. So the coding is going to be a lot more complicated. But as far as resources are concerned, it's not that crazy. It's not that crazy an idea. So let's talk a little bit about GeckOS, starting with its history. How many people here know who Andre Fachat is? He's the guy who wrote GeckOS. I see a few hands going up. I would expect more. But Andre, of course, is known particularly as an expert on the older machines like the PETs and so forth. And I would expect that at the Toronto PET users group, there would be people who know who he is. But anyway, Andre works for IBM over in Germany. And he originally wrote GeckOS to run on a machine that he built himself. He built a 6502 machine. And that machine had a memory management unit and supported up to 1 megabyte of memory. So it didn't have quite the restrictions that you would see on, for example, a Commodore 64. But he did later port it to run on some of the Commodore machines. It'll run on a PET, even a 32K PET. It'll run on an 8296, which of course is the most beautiful machine ever created. And it'll run on a Commodore 64, which is what I'm going to talk about. So as I talk about the details of this, just bear in mind that they might be slightly different from one version to another. Now, development on GeckOS is extremely active lately, especially within the last month or so. And I think it might be partly my fault that this happened, because as I was studying GeckOS and learning it and preparing for that first presentation I gave at VCF Midwest in Chicago, I was corresponding with Andre, and I was asking him questions and stuff, and every so often he'd say, well, you know, I really should get back into GeckOS. Well, he has, and everything is changing really fast. If you look at the commits on GitHub, there's just this long list lately of things that have been changed and improved and added. So the source is GPL. It's freely available. It's on GitHub. There are the coordinates to Andre's repo. So if you want, you can check out the latest branch or the latest stable release and build it yourself and run it on your own machine. It's trivially easy to build. Well, assuming Linux it is, but it's really not hard to build it at all. In fact, when I do my demo, I'm going to do a clean and build of the entire operating system beforehand. You won't believe how fast it is. So let's, oh yes, I have one more picture here. This is one version of the machine that GeckOS originally was written to run on. Wouldn't you love to have something that looked like that? I love that picture, jeez. And this is the one with the MMU and supporting 1 megabyte of memory. Anyway, let's now talk about the features of GeckOS. Now, looking at all the stuff on this list, again, you might be forgiven if your mind goes back to that other slide and you start thinking, are you crazy? But honest to God, it's got all these things, and I'll be demoing most of them in just a minute. First of all, GeckOS is a preemptively multitasking operating system. It really is. It's not some trick or anything. It's really preemptively multitasking. It's got a scheduler that runs at interrupt time based on a timer interrupt. In fact, not only is it multitasking, preemptively multitasking, but it's got task priorities. The kernel has a renice API so that you can drop your priority and let somebody else run more. It's even got multi-threading. So by default, every thread, or every process, every task that is, has one active thread. But you can start other threads, or you can just fork a new task. It's got virtual consoles. Now, Linux users are probably familiar with this. On Linux, if you go Control-Alt F1, it drops you down to a full-screen console, and you can go Control-Alt F2 and so on. And Linux usually ships with a half a dozen consoles. There are 4 on GeckOS, and you can just tap F1 to cycle between them. It's got signals. One process can send a signal to another process. It's got semaphores, which are very important in GeckOS because of the lack of hardware protection. So you have semaphores that are defined by the operating system that refer to, for example, a certain area of memory or a certain device or the serial bus in general. And a lot of the kernel APIs require you to lock a certain semaphore first before you call that API so that nobody else gets in there and does something he shouldn't do. And again, that's because there's just no protection against this kind of thing on a 6502. The shell has both backgrounding and redirection. I'll be showing those. It's got piping. Piping, as far as I can tell, was broke for a long time, and Andre just submitted some patches to get it to work again, but that was like literally within the past couple days, and I think it still has an issue with certain programs, so I won't be showing that. but I'm sure it'll get fixed within the next few days. It's got environmental variables. I'm not going to show that either, but there's a single environment on the Commodore 64 version as opposed to an environment per task. And then it has a relocatable file format, which is something that Andre came up with. And of course, that's very important in a multitasking operating system because you don't know where your program is going to load. Okay, your program might load here today, and tomorrow there might be something else running there and it loads over here. So you can't have any absolute addresses in your executable. What happens is when the system loads a program into memory before it runs it, it does an address fix-up based on the load address so that all the addresses match up. And, so that's very important, and that'll come up again later in the discussion. So having said all this wonderful stuff and bragged about all the stuff that GeckOS can do, I guess I better put my money where my mouth is and do a demo. So I hope you don't mind. I'm going to do the demo using Vice. But Leaf and I worked it out so that we're going to have the disk drive sounds from Vice. So it's going to be closed, but not a real machine. The thing is, if you're doing operating system work on a Commodore 64, you pretty well are going to have to use cross-development tools and emulators anyway because it's just too unwieldy otherwise. I'm normally very disapproving of that sort of thing, but you know, all bets are off with an operating system. So here's what I'm going to be showing, and like I say, this is a very recent build of GeckOS. It's not the most recent build because I had to cut it off, I think Monday or so, because things were changing so fast. I just needed to know what version I was going to be running. Yeah, and here's all this stuff I'm going to be showing. The highlight is going to be, most of this stuff has been in GeckOS for years now, but the highlight is going to be the new PS and kill commands. And I'll show how those were developed and how they weren't developed. You'll see what I mean by that. So let's go over here, and I've got Vice running. Did I do this? Yeah, I don't want this guy full screen while this guy is full screen. Okay. So I'm going to, actually no, I said I was going to build it from scratch, didn't I? So let's do this, and then let's do this. I've got a little script I use, and I'm going to do a complete clean and build of the operating system and then bring it up in the Vice monitor. That should take a long time, right? Or not. That was it. Now when you start GeckOS, there's a basic loader that loads a large kernel image, and then it loads a little tiny machine language. Yeah, you'll like this. Then it loads a little tiny machine language stub and passes control to it, and that little stub disperses the kernel image into upper memory above and below the I/O area, and then it starts it up, and then the magic begins. Here we go. There is our boot screen. So now we have a really real Unix-like operating system running on a pretend Commodore 64. Notice when it starts up that there are 5 things starting. Okay, there's init. There are 2 file system device drivers. There's one that controls the devices and one that's specifically for the IEC bus. And then there are 2 shells. The one says shell and the second one says LSH, which stands for library shell because it has to do with the standard library. Now, that older shell is considered more or less obsolete and it's not really supported anymore, but it still has, or had until recently, features that weren't in the new shell, which is the one that we're looking at now. So that stuff is gradually being ported over to the new shell, and I think at some point that older one is going to be deprecated. But where is that older shell? We're only seeing one, of course, you know. Well, remember I said it has virtual consoles, right? So if I tap F1, oh, there it is. There's the other shell. That's the old one. Nothing on 3, nothing on 4, so let's go back to 1. And that older shell, you know, they're both loaded at boot time, and that older shell actually even includes, whoops, a built-in machine language monitor. So you know, you can imagine that it's using a lot of memory, right? So that's not a small piece of code there. But let's go back to that first shell, and I want to show you that GeckOS has a lot of the things you would expect in a Unix-like operating system, starting, of course, with ta-da, for real. And of course, you can do something like this. And there you go. The file sizes, of course, are actual number of bytes used on the disk, not the file size itself. It's number of sectors used times 256. Right? And you know, it even has, I'm not sure on what device this would be applicable, but it's got, you can put more L's on it and get a display with more stuff. And this is kind of like the full Monty version of LS. And we'll see, yeah. It's, out of 1541, of course, most of this doesn't even apply, but yeah, it's there. It's there. So you can also do something like, for example, this does what you would expect. Okay, for those who don't know, Wizard is my cat. He's the best cat a boy ever had. He's never, ever naughty. Right? And remember I said it has redirection. Well, this will work. Okay, you hear the disk drive running because it's writing to a file now. Nothing came out on standard output. And of course, if we want to see where the output went, we can cat that file. And the output went exactly where we would expect it to go. So you can look through the directory and play around with some of the other things it's got. As of very recently, like the past few weeks, it's now got a more command. It's got a WC command, a word count. So there's a lot of other stuff. But I'd like to show some demo programs that I wrote for GeckOS that are showing the more internal features of it that I was describing before. And there are 3 little demos, all of which involve 2 programs. The first program is going to fork a second program when it starts, and then there's going to be some interaction between those 2 programs. So the first one demonstrates forking and multitasking. So I have these 2 programs. This program, when it starts up, is going to fork a second program, and that second program, named fork, is going to start flashing the border slowly. Well, we see the first program is still running. Eventually the first program ends, the second program is still running, and eventually the second program ends. So you can see that the multitasking is very smooth. We had a constant pulsing of the border when it was changing colors and everything. So everything, the multitasking works extremely well. Second demo is signal passing, sending a signal from one process to another. So this first program, the 2 programs are sig send and sig receive. The first program forks the second program, and when the second program starts, he's going to register a signal handler. It says setting mask there, and it just scrolled off the top. But the first program, meantime, printed a message saying, hit a key when you want me to send a signal, right? And then that second program, he's just going in a timer loop waiting for that signal to be sent. So if I hit a key, that first program sent sig user 1 and then ended, and the second program received the signal. So that has all kinds of interesting possibilities. There was a guy at the Chicago show, he said, I'm going to write a battleship game that uses signal passing to get to do the stuff. Right? And then there are the third demo is the semaphores, and I talked about the importance of semaphores. So here's an example of that. First program, immediately when he starts up, he's going to lock an arbitrary semaphore named semdemo. Then he's going to fork that second program called semwait. And of course, the first program says, by the way, hit a key when you want me to free it. But meanwhile, he's got a lock on that semaphore. And the second program says, well, okay, I'm waiting because the second program is trying to do the same thing. He's trying to lock that same semaphore, but of course, he's going to get an error message saying, no, that semaphore is in use. So when I hit a key, the first program frees that semaphore and then ends. And when the second program comes up and gets his slice and gets a chance to run again, he's going to try again, and this time he did acquire the lock. And of course, when he's done, he frees the semaphore and ends. So if you're going to write programs for GeckOS that involve semaphore locking, make sure you release the semaphore afterwards, otherwise there will be pain and suffering. So those are the demos that I wanted to show, except that there's one more demo. That forking and multitasking demo, there's another version of that demo, because when I first got that running, I was so excited that I actually made a video of it. I posted a link to the video in IRC. And Leaf saw that video, and he said, well, that's all well and good, but what you really want to do is background the whole demo and then take a directory listing while it was running, right? And my reaction was basically, you know, are you crazy, right? But I thought, you know, what's the worst that could happen? I should try it, right? And with GeckOS, you'll see that happen over and over again. You might come up with some crazy idea and think, well, that wouldn't work, but you try it and it does work. It happens all the time. So I'm going to do a slightly different version of what I call the schema demo. And instead of taking a directory listing, I'm going to ask for a process list, which is a good segue into this new PS program that we have. So here's the forking demo again. And this time, I'm going to background it. And when I get my cursor back, I'm going to ask for a process listing. So their forking is running, the second program is flashing the border, and we have a process listing, and then one by one the other programs end. This guy's still running, yeah, okay. All right, so we had, and I don't know what the error message is, that's something that came up recently. It doesn't hurt anything right now, but I'll figure it out. At any rate, look at this process list. This is a thing of beauty right here. We have on the left-hand column the PID, the process ID, and as it turns out, the process ID is actually an index into the task table. So by looking at it, we can see that the task table has 12-byte entries because it goes up by 12 every time. And then in the second column, of course, we have the name of the process, which you need to know. And then you have, and by the way, that name is new, that didn't used to be there. Then there's the exec address, which is also new. And you have to know the exec address of your program to debug it. Because remember before I was talking about how you have relocatable programs, and you don't know what the addresses of your routines are until the program gets loaded and relocated. So you might have, you know, say you have a routine called, you know, My Groovy Routine, and you want to put a breakpoint on it. And you assemble your program and you look at the listing and it says, well, My Groovy Routine is at 0100. Well, it's not at 0100, it's at offset 0100 from the beginning of the program. So you have to take the load address of the program, add the offset, and that's where you set your breakpoint. So you need to know the exec address. And again, that's something new. Next column is number of active threads. Remember, by default, I said that every task has one active thread. And then that next one is really interesting. I love that next column. It's parent PID. Okay, so the first one, init, of course, as we know, is the father of processes. And he really has no parent. He gets started up by the kernel at boot time. So he's got a parent of FF. And remember when we saw GeckOS starting and there were 5 things that started up? Init, 2 file system device drivers, and 2 shells. So we can see that those are the first 5 entries. And those second 4 all have a parent of 0, which means they were started in turn by init. Now we see that 30 is the shell, the one we're looking at, and I started forking from the command line. So forking has a parent of 30, which is the shell, and forking, forked, oh geez, and forked therefore has a parent PID of 3 Charlie. Okay, that makes sense. And then when I got my cursor back, I typed PS at the command line, so PS has a parent of 30, the shell, not 30, but 30. So that is very interesting information to have. SM is the signal mask for passing signals, so it's what signals a program is prepared to respond to. And SIG A is the signal handler address, in other words, the address that gets jumped to when a signal is received. Those last 4 are all the same because, and I just learned this, the standard library actually multiplexes those and they all go to the same place and then it fans out from there. And then of course we have the input, output, and error. So I'm going to talk, the GeckOS part of this talk is how we got the name and the exec address in there, which didn't used to be in there before. And I'm going to take one slight detour to show you the kill program. which was in the old shell too, but it's got a few more features now, and I'm the one who did the porting, and I got it accepted into the kernel, into the master branch, and I'm very excited about that. So what I'm going to do is I'm going to go over here, and I'm going to start up the second half of that signal passing demo. This is the program that sits here waiting for somebody to send it a signal and just goes in a loop going, hey, I'm here, I'm waiting. All right, let's go back here. Now, who knows what the kill command does in Unix? Yes, sir. Kills a process. Man, put on the dunce cap and go sit by the principal's office. Sir.
Sends a signal.
Sends a signal, exactly. Now, by default, it sends a signal that will probably kill the process that's receiving the signal. It sends by default sigterm. Sigterm, yeah. And that may not kill the process, depending on, if it's gone wild, it may not kill it. So in that case, you might want to send a sig kill, which of course is signal number 9, which is where we get the expression kill-9, which even little girls who go to Jurassic Park know how to use, right? So the original version of kill in GeckOS just did a kill, and I changed it so that it could send any arbitrary process. So let's go over here and look. Oh, yep, still waiting. So let's send him a signal, but first we need to know what his PID is. So we'll take a process listing, and we'll see that there is sig receive. He's at 3 Charlie. So I'm going to set a sig break signal to the process 3 Charlie. Well, let's get over there and watch this happen. Aren't those consoles wonderful? And we'll see that, in fact, he did receive a signal 1-0, which happens to be sig break. Great, it worked as expected. Now I'm going to start him up one more time. And this time, and he's going to have the same PID. He'll get the same slot over again. And now I'm going to send him a kill-9. Now, as it happens, 9 is not the number for sig kill in GeckOS, and in fact, sig kill is not even implemented in GeckOS, but that's okay. Kill-9 is tradition, right? So, yeah. If you send him a kill-9, well, let's watch and see what happens. Boom, he's done. Put a fork in him. He never even prints a message saying, I got a signal, because he didn't get a signal, he just got his head chopped off. That was the end of it. Okay. So that's the new stuff that's in GeckOS, this PS and kill command, and now comes the kind of heavy-duty part of the talk where I talk about how we got there, how we got those new fields in there. Push the wrong button, I guess I did. This is where we were. Okay. So to understand how the name and the process, the name and the exec address were added, we have to understand first how the PS command works in GeckOS. So here's the old one, first of all. This is from the old shell, and this is an earlier build of GeckOS. This is the 2.09 release that came out in 2013, I think. What's wrong with this picture? Well, first of all, we don't have any names. Well, we do have one name, but what's at PID 0? I guarantee you it's a nit. Trust me. Hey, buddy. I guarantee you it's a nit, right? It's not the shell. It's a nit. So there's something there that could be improved, and we don't have the start address of each process. Like I said, if you don't have the start address, you can't really do meaningful debugging. There are other ways around that, but they're a little fuzzy. So let's talk first about how the PS command works. Now, all this information that PS printed out comes from the kernel's task table. But it's really not appropriate for an end-user program like PS to go sticking his fingers in the task table. That's kind of forbidden fruit, as it were. The kernel shouldn't, you shouldn't be sticking your fingers in the kernel's data structure, basically. But on a 6502, there's no way to prevent that. Your program could, by adding the right include files, figure out fairly easy where the task table is, right? But you shouldn't do it. You can't prevent it, but you shouldn't do it. So what happens is that there's a kernel API called get info. And that's what PS calls. PS calls into the kernel, he calls get info, and get info says, okay, I'm going to look at my little task table here, and he grabs the information, and he builds a table someplace for PS to read. Okay? Well, that's part of the story. The place he builds that table is called the Program Communication Buffer, or PC buff for short. Remember what I said about semaphores? You could have other processes that are making kernel calls that use that PC buff at the same time. That would be a bad thing, right? So what really happens is that the first thing PS does, he locks the semaphore that refers to the PC buff. Then he calls into the kernel, he calls get info. The kernel looks in his task table, builds a table in the PC buff, PS reads it, and prints the results to the screen. So that's the way it works. Now, how do we get the name and the start address from the task table into the PC buff? Well, I looked at this and I thought to myself, I bet I can code that. I could do this. But I'm still pretty leery of the GeckOS kernel because it's quite complex. It's really quite complex. And so I thought to myself, maybe I could add this stuff by just changing get info and the way get info works and not actually touching the rest of the kernel itself. And that would make it easier, right? So if you've ever done any amount of programming, you know that kind of thinking invariably ends up with something that's 10 times as complicated as what you originally wanted to do. But that's what I did. So I thought to myself, okay, I've got two classes of programs I want to get the name for. One is the standard library programs that are started by the shell, and the one is those 5 programs that we saw started by the kernel when it started up, the device drivers, the shells, and init. So for the standard library programs, I did a little digging, and I found that in the task table, one of the entries is a pointer to another table. It's a per process table that's used by the standard library, and it contains, among other things, the name of the program. So I'm like, wow, that was easy. I'm home free. All you got to do is when you call get info, he follows that link to the standard libraries table. He pulls out the name, plops it in the new field in the task table, and we're all good, right? Well, not really, because just like user programs shouldn't be sticking their fingers in the kernel's data structure, the kernel shouldn't be sticking his fingers in the standard library's data structure either. And that's one of the things about GeckOS. It's written properly. Everything is done right. You could kludge your way around this like I was trying to do, but it's not the right way to do it. The kernel, there's a reason we call it the kernel, right? The kernel means like the core, the seed of something, and it should be an entity unto itself and not even care or even know about the standard library. It shouldn't even have to know there is a standard library. So that's not a good idea. It works, but it's not the right way to do it. All right, shot down on that one. Then we have, where I really went off the rails, we have init and the device drivers and the stuff that gets started at boot time. Well, I had a look at how the operating system starts. And the way it starts is that you have this big kernel image in memory, and at the beginning, there's a header followed by one of these programs. Then there's another header somewhere else, followed by a program, and another header somewhere else, and they're in any arbitrary order. You can't control what order they're going to be in. But each one of those headers points to the next one. It's a linked list, right? So I thought, well, looking at those headers, I see that, guess what? The name is in the header, FSDev, FSIEC, init, whatever. So I thought, well, if I walk through those tables, I can just grab the name out of there and I'll be good, right? No, it doesn't work. It doesn't work, and the reason it doesn't work is that the kernel has it works, but the kernel has a fairly complicated way of going through things. The question is, how do you get the right one of these programs with the right process ID? And the only way I could think of to do it was to walk through those tables in the same order that the kernel does when it starts up. Now, one of the things in the header is a program type byte, which is a bitmask. And what the kernel does is it walks through there and it starts certain programs in a certain order. I want to start for a program that's of type init. I want to start a program that's of type file system driver, right? And it makes multiple passes going through all these programs. So what you'd have to do is you'd have to go through there in the exact same order that the kernel startup does and make multiple passes, but if you do it in exactly the right order, the names you come up with will match up one-to-one with the process IDs. Oh boy. Okay, at this point I'm really off the rails because this is just not something you should do. Andre looked at that code and he said, I had to look at that for quite some time to figure out what you were even trying to do. So did I, in fact. So yeah, that works, but it's a filthy kludge. Apart from which, if the way the kernel starts changes even slightly, that whole thing's going to fall down on its face. So, okay, both types of programs that I was looking for the names for, I came up with solutions that actually worked or seemed to work, but it was just the completely wrong way to go about it. And as it turns out, going about it the right way by making subtle changes to the kernel turns out to be much easier. And these are the patches that Andre did, and this is what's in GeckOS right now. So, as it turns out, of course, every single process that starts on GeckOS has to go through the kernel fork API. Fork is what starts a new process. It allocates another entry in the task table, it creates a stack, it does all this other kind of housekeeping, and then it passes control to the new process. And guess what? What are the parameters you pass to fork? Among other things, a name and an exec address. So it's already there, the kernel's already got it. So all the kernel's got to do is plug that value into the new fields in the task table when it starts a program, right? Easy. Should be easy, right? Nope. Nope. And the reason that's not easy is because standard library programs pull a little trick. They put a stream number in the first byte of the file name field, and the file name actually starts in the second byte. So if you let that go, every standard library program would have an unprintable character at the beginning of the file name. But as it turns out, there's a very easy, and by the way, more on that stream number that it's passing that way later. But as it turns out, there's a very easy fix to that because the standard library was not using all the possible parameters that the fork routine takes when you call it, and you could use one of those parameters to pass that stream number. So that works out okay, and this was all fairly straightforward. I looked at the code when it was committed and I was like, oh, why didn't I think of that, right? And then adding the ones for the kernel programs, that's simple because they're already there and they're already perfect. The only exception being that init originally actually went out of its way to put a null byte in the name field. But there's no reason it should hide from the world, right? Now, adding the exec address. We've got the name thing solved. Adding the exec address. Let's see. The exec address is also passed to fork. So again, you could just plop it right in and it would work. Well, for the program started by the kernel, that's true. But again, we have an issue with the standard library. Now this one's really crazy. Yes. The reason that's not quite going to work with the standard library is that the way the standard library starts a program is that it does the little housekeeping stuff, it calls fork to create a new process, and then after that call, it loads the program from disk and relocates it and passes control to it. What's wrong with that picture? How can it load and run the program if it's already called fork, which starts the process? It hasn't even been loaded from disk yet, right? But here's how that's done. Here's the code that in the standard library to set everything up and call fork, and as a start address, he passes the code a little bit further on in the standard library, which does the loading and the relocation. So he calls fork, fork sets up a new process and everything, and then passes control to it with the address given, but the address given is within the standard library, which is the routine that does the loading and the relocating. But as far as the kernel is concerned, the new process is already running, except that it isn't because it's the standard library. But once he loads the program, relocates it, now he knows the start address, he passes control to it, boom, and we go, oh, well, this is great. how about if we wedge in some code right at that point when he's done loading and he's about to pass control, because now he knows the start address. Fine, plug it right into the task table. No, the standard library mustn't stick his fingers into the kernel's task table, right? Again, we have that problem. So the solution to that one turned out to be that Andre added a new API to the kernel called setInfo. Now we have getInfo and we have setInfo. And setInfo allows the active task to set its own start address in the task table. And remember, the active process at that point is really not the process that's going to start. It's still the standard library, which is loading, because it called fork with its own address, and fork thinks the new process is starting, and it gets this far, it knows the address, it plugs it in, and then it jumps to the program, so it all works out anyways. I don't know if I explained that well or not, but this is pretty crazy stuff. But this is the kind of stuff that you experience when you're dealing with, something on the operating system level. And even something like GeckOS that runs on a fairly small machine, there's a lot of complexity there. But it was a lot of fun, and there's the solution. We have a setInfo API now. So this is great stuff. This is wonderful stuff. And now that we have this PS and kill, we can do almost anything because we can debug our programs beautifully. In fact, it's a new golden age of GeckOS, I like to call it, because now all of the things that have been on the list can be moved forward. First of all, I think there's little, if anything, that's still in the old shell that's not in the new shell. So it could probably be deprecated pretty soon, and you just have the new shell. You might still want to have two of them running, right? But you wouldn't have to have that old shell with the machine language monitor built in, which, by the way, you can load from disk even now. Another thing, what are some things we could do with GeckOS? We could have better support for CMD hard drive. Okay, so remember that long listing I showed you with the file timestamp and everything? Well, CMD hard drive has a timestamp, but GeckOS doesn't know where to find it, so that would be interesting. The one that interests me most is, imagine, how many people are familiar with 1541 Ultimate 2 Plus? A lot of hands go up, okay. That machine, as you know, has an Ethernet port, and what might be a little less well known is that there is an API that you can call. You can push some registers and stuff, and you can actually open a socket and talk to another machine, and you can write your own networking programs. Imagine a device driver for the 1541 Ultimate's networking capabilities within GeckOS. I don't know if I have the chops to do that, but I'd like to try it. Another thing, you may have noticed that the disk access is not particularly fast in GeckOS. It doesn't, of course, have Jiffy DOS, but maybe there's a way to speed that up. And there's some other things involved too, involving buffering, and those are known issues that might get worked on later on down the line. But it's a big deal. And of course, your project here. What I found when I gave a talk on GeckOS in Chicago was that all these people kept coming up to my table and saying, "Oh wow, I could do this." Like the guy who said he wanted to write a battleship program. Imagine all the different stuff you could do. So if you're interested in working with GeckOS and writing your own programs for it, if you know 6502 assembly, it's not hard at all. If you look at those demo programs I showed, all of the stuff that actually was happening in those, like the forking and the signal sending and the semaphore locking and all that stuff, it's all just a few lines of code. And most of those programs are like waiting on a timer loop, printing stuff to the screen, error handling and all. It's like 90% fluff and just a few lines of code. So it's really easy to write programs for GeckOS, and if you're interested, have a look at it. Here's the resources slide, and I'm going to post these slides on my website right after I get back to my table. But the bottom one is interesting, and that is the commentary that I wrote on the internals of GeckOS, which is not finished and will never be finished because there's so much to learn. But this, the name, of course, is a play on words from Professor Lyon's commentary on Linux, right? So I wrote this commentary, and it's a very detailed description of the internals of GeckOS. It tells about what happens when the operating system is started. It talks, I'll post this on my site. It talks about what happens when the operating system is started, how the scheduler works, how programs get loaded by the shell, and all this different stuff in immense detail with file names and line numbers. So if you're interested in learning the internals of GeckOS, have a look at my commentary, and that'll help you get a leg up and learn your way around, so you can probably go further than I did. Okay, having said all that, we come to this slide that says questions. Does anybody have any questions about GeckOS? Yes?
Would it be even hypothetically possible to get something like CC6502 building GeckOS, like relocatable images?
Are you
like the C compiler that
you're talking about doing it in C?
Yeah.
Yeah. The question was, is it possible to write programs in C for GeckOS using CC65? I guess all I can say is good luck with that. It would require CC65 to know how to generate an executable in that relocatable format.
Right. That would be the main task,
yeah,
right?
Yeah. I guess it would. I mean, I don't know. The answer I gave in Chicago, I got the same question in Chicago, and the answer I gave is that, well, real men code in assembler. But yeah, it's theoretically possible. Yeah. Anybody else have a question? Okay. Yeah. Oh, yes.
What's the roadmap for that? Any like C128 portability there or anything like that?
Yeah, that's another question that came up, and somebody asked about Atari and Apple II and all this other stuff. Theoretically, you could write it for almost any 6502 program. And if you look at the source code, there's a directory called Arch. So there's Arch C64 and Arch PET and Arch 8296 or whatever. There's also an Arch Proto subdirectory that has basically like a clean slate version of what you would need to do to port to a new architecture. But I don't want you to have any false hopes about that, because it would not be straightforward. It's certainly doable, but I have, by the way, a complete printout of the GeckOS source code back at my table, heavily highlighted and penciled in with markings and stuff like that. And if you have a look at that, you'll see that it's just littered with a lot of defines and if-defs and so on and so forth. So it's already fairly complicated, and adding additional architectures, while certainly possible, it would not be a small undertaking. But yeah, it's certainly possible. You could write a version for the 128 or the whatever 6502 machine is out there. Anybody else? All right. In that case, thank you very much for your kind attention, ladies and gentlemen. I hope it was a good idea.